or I can come round that side and you can come from there. To where? Right, let's see what I can do. Hello. This brief in the series to challenge the thinking is titled Climate Change. The answer is Bullocks. I'm Dave Stanley and this is Laura, and that's her 1-month-old calf Paula. Laura is a pedigree Lincoln Red, a traditional British breed renowned for being low input and producing top quality beef. These are pasture or only grass fed and produce this well marbled beef which is renowned for its flavour and also very healthy. So what's the problem? Well, the problem is this: there are many that will turn around and tell us that we're actually stood amongst the climate change's biggest criminals. Why? Well, all that grass, when it goes into the stomach, is broken down by a process called enteric fermentation, which then releases methane, which is 20 times more powerful than carbon dioxide, hence the problem. However, in this brief, what we're going to do is take a close look at what goes in the front end, what comes out the back end, and then dig a little deeper than most. And I think you might be a little surprised by what we find. But one of the messages will be, beware single issue environmentalism. First, a few definitions. Intensive rearing, I'm talking about animals that are predominantly reared indoors, being fed on straw, maize, and supplementary feeds consisting of barley, wheat and soya. Extensive, I'm referring to animals that are largely grass or pasture fed, predominantly kept outside and may have some supplementary feed. And arable monoculture, I'm talking about farming systems that are in continuous cropping with no break of pasture or clover lays and no livestock involved. One of the important inputs to intensive system is soya. Brazil is the largest exporter of soya, and they have been clearing rainforest there, a couple of large bulldozers dragging chains between them for the production of this soya. The growing the soya involves inputs of pesticides, fertilisers and the tackle associated with it. The soya that would then be harvested, costs involved there, and then transported by road to the nearest port, loaded onto ships, sales to the UK, unloaded and then transported to a mill where the soya would be processed into feed. From there it would then be transported to the farm and would be part of the system, the feed system, where it was supplemented by straw, barley and so on. Now quite clearly the inputs to this system are high in energy, fossil fuels, and also high in economic costs. If we take a look at an extensive system, and here we've got some Welsh blacks on the hills, then the inputs to this grass, or the ecosystem, or landscape if you will, is essentially low input. Low in terms of energy, and also low in terms of costs. Well, what about the greenhouse gas emissions if you compare the two? Well, let's take a look at the English Beef and Lamb Executive, who've done a carbon footprinting of beef production in England and compared lowland, predominantly intensive, with hill and upland suckler beef, largely extensive. Here on the yellow column I have recalculated the energy inputs, so they're in more recognisable form in terms of gallons of diesel or litres per kilogram of beef produced. And you can see basically each kilogram of beef requires about 1/5 of a gallon of diesel. Now if we take a look at the greenhouse gases associated with the two systems using the 100-year figure, then surprisingly there's hardly any difference between the two. Some of this is explained though by the exchanges that take place between the uplands and lowlands by way of transfer of calves and lambs and so on. But also the energy inputs to the two systems are almost identical as well. Now, the reason for this greenhouse gas similarity is because the extensively reared animals will typically take twice as long to rear. So, as you'll remember from the energy and climate change brief, methane from cattle is some 20 times more powerful than carbon dioxide and is a predominant factor in terms of measuring the greenhouse gases. So the longer the beast lives, irrespective of the inputs, the greenhouse gases rise proportionately. If we take the 20-year figure for methane, then as methane has a very short life in the atmosphere of some 12 years or so, the global warming factor for methane then goes up to 72. And the difference then is that the extensive system produces 80% more methane or greenhouse gas emissions than the intensive system. And most of you will probably have heard of this FAO report that was produced about 4 or 5 years ago, Livestock's Long Shadow, where they identified that cattle globally were responsible for 18% of the greenhouse gas emissions, exceeding those of transport. What's not generally well appreciated is that this report actually advocates greater intensification of livestock production. In other words, more of the intensive and less of the extensive. You'll probably be aware of the drive to eat less meat and reduce the number of stock. Well, let's just take a look at the number of ruminants in the UK, and for 2002 the figure was 8.6 million cattle and 34 million sheep. But it just so happens I've got the encyclopedia for 1876, and the census figures there show that 130 years ago there were 6 million cattle in the UK and 28 million sheep. And one beast is worth about 6 sheep in terms of the inputs and outputs and the greenhouse gases. If we take a look at North America, then the US Department for the Interior report that in 1800 there were some 80 million bison roaming the American prairies. In addition to that, there were some 16 million antelope, and the figures for deer and moose I couldn't ascertain. Today, the US Department for Agriculture reports that there are now 93 million cattle in the US, to which you can add another 13 million in Canada. There's some 7 million sheep, 4 million goats, and 20 million deer. Now, if you do a quick calculation on that, you can see both add up to about 140 million ruminants, 1800 to the year 2010. Not exactly planetary changing differences there. If I could have found the data, I would suspect it would be a similar story for Africa. South America and Australasia would be a different story, however, where there were few, if any, ruminants. But what about the inputs? The inputs to the bison would consist of the ecosystem and the sun, and for the cattle, again, it's going to be solar, plus the fossil fuels, the nitrate fertilisers, the pesticides, hormones, antibiotics and GMOs, etc. The output, or one of them, is obviously food, beef in this instance. However, all beef is not equal. There are numerous reports to be found highlighting the significant differences between beef which has been grass or pasture fed and that has been intensively reared. And the difference lies in the ratio of the omega-6, the bad news fats, and the omega-3, the good news fats. Fundamentally, there is a fifth of the level of omega-6 fats in the grass-fed animals. Outputs from the bison, it's just going to be the ecosystem again. On the other hand, for the cattle, it's going to be actually a loss of ecosystems. There's going to be significant emissions associated with the loss of soil organic carbon, and there's the pollution of the air and the rivers. from the effluent and the slurry and the resulting maritime dead zones. Also, of course, there's some very significant greenhouse gases. So basically, if you look at the two systems then, as we've seen from the numbers, the methane associated with enteric fermentation is going to be broadly the same. The difference lies, though, in the inputs. Very significant on the cattle rearing side and very significant negative environmental impacts associated with the outputs. One is clearly sustainable and the other somewhat less so. Fundamentally, the changes are down to the way that the animals are reared, to the land management, not to the cattle themselves. With that in mind, it should be noted that the United Nations FAO are estimating that in order to meet the demand by developing nations for more meat, by 2050 livestock numbers could double to 2.6 billion. Much of that will be met by intensive rearing with the high inputs of fossil fuels, and for which the feed will take about 1/3 of the available agricultural land. First, the carbon cycle. The plants turn around and take up water and nutrients from the soil, and through the process of photosynthesis, taking carbon dioxide from the atmosphere, emit oxygen and turn it all into carbohydrate, which then acts as a food for the animals and also for human beings. The animals and the humans then consume the food, the carbon's burnt off goes the carbon dioxide, and in the case of the livestock, the ruminants, you're not only getting off the carbon dioxide, you're also getting off the methane. What's of note, though, is that there's a recent report from Sydney University that has analysed grasslands and has noted that the uptake of methane by the grassland far exceeds that is emitted by the livestock through enteric fermentation. Another part, of course, is that to complete the cycle, the urine, excrement, detritus should then be returned to the soil and go round the loop again to act as nutrients for further plant growth. On the numbers side, we have 6.7 billion people, forecast to increase to 9 billion, and currently there is 1.3 billion cattle. This is from the European Nitrogen Assessment, where it shows the ecosystem and the inputs and outputs of nitrogen. It shows agriculture as separate from the ecosystem, and the major inputs to the separate agricultural system are obviously nitrate fertiliser, synthetically produced with very high fossil fuel inputs, and that's about 70% of the inputs. There's about another 20% associated with airborne deposition from fossil fuels burning in power stations and vehicles, and this shows about 8% going in from the biological fixation of nitrogen through legumes. Interesting to note, though, for the world as a whole, it's reckoned that there's about 24% nitrogen input to agricultural systems. Obviously, in other parts of the world, they're not so dependent upon nitrate fertilisers. But an important point to note here, though, is that this is a totally natural process, the fixation through legumes. And indeed, if you go to any of the upland areas, you'll find a vast amount of clover, which is fixing the nitrogen and obviously emitting nitrous oxide at the same time. If food production is to be sustainable, agriculture should be an integral part of the ecosystem. And then the biological fixation of nitrogen in the farming systems and the arising nitrous oxide would be part of a natural process, and therefore should not be counted under IPCC, because the effect of that is that it turns around and discriminates against sustainable farming methods. Now let's take a look at the UK agricultural emissions, and you can see here that 35% of the total emissions are attributed to enteric fermentation. These emissions of methane are actually part of the natural carbon cycle, then those should not be included. What you then have is that 53% that's currently attributed to agricultural soils increases to 80%. And I'm suggesting that if we're to seriously address the agricultural emissions and their impacts on climate change, then the focus should clearly be on soils, not on cattle. This slide shows the IPCC global carbon stocks, and whilst it's probably too small to see, what it actually shows is the total carbon in vegetation, total carbon in soil, and if you tot up the total carbon in the grasslands, tropical and temperate, it comes to some 630 gigatons, of which 90% is in soils. Now, from the Energy and Climate Change briefing, you'll remember that there's about 6 gigatons of carbon dioxide emitted arising from the burning of fossil fuels. So what this boils down to is that if we were to achieve a 1% per annum increase in the existing carbon stocks within the soils of grassland, we can basically offset that's emitted on an annual basis by fossil fuels. You might like to compare that option with some of the others that are being talked about in terms of carbon capture and storage, where there's a vast capital outlay associated with the kit that's going to be or might be installed on power stations, and then there's a huge losses associated from the reduction in efficiency. And compare that with the option of capitalising on a natural cycle. Here you see the many insects that feed off cowpats. What you probably can't see is the very small flies that are crawling all over this. But what it does demonstrate is the significant food chain that's supported. Let's go a little deeper and look underneath the cowpat. This one has already been partially turned over by starlings and probably rooks as well. As we look through, there's one worm there, 4, and here's some lice, which presumably is what the starlings were after. There's some insects running around, and you can see from that worm that's now gone back down again, these will have been coming up and pulling down the organic matter, i.e. the carbon, back into the soil, and along with it the nutrients, which will then obviously help fertilise the soil and encourage a fresh growth of grass. The grass contains a wide range of species of grasses, legumes and wild flowers. And in addition to the cattle, it also supports a diverse ecosystem, biodiversity, which also serves to enhance the wildlife food chain. And indeed, a couple of years back, a pair of barn owls moved into residence to capitalise and feed off it. In the barn underneath the nest box, there is one dead mouse that obviously dropped down and the owl couldn't recover, but also there's all these pellets that are regurgitated by the owls, and if you open them up, they contain the fur and bones of small mammals that have been consumed by the owls. And there's one skull there, and another there. And typically, if you go through, you'll find there's 2. In fact, there's a third. 2 skulls per pellet. These mice, of course, are part of the food chain that is supported by the pasture land, but of course starting back in the soil. Let's dig a little deeper again and find out what else has been going on in the soil. In this block there are 3 grass fields, and if you were to just take a look over the hedge, you'd turn around and say it's grassland, and indeed DEFRA would just classify it as permanent grass. But the history of these 3 fields is actually quite different. The most northerly one, been within my control for 20 odd years, classified as historic meadowland. Best of my knowledge, it's never had any chemical fertilisers applied to it. It's got a wide range of grasses and flowers in it, including orchids. Immediately to the south of that is another field on exactly the same soil, which would be classified as improved grassland, in that it has had, up until 2001, regular applications of nitrate fertilisers and may well have had herbicides as well. And the sward there consisted of coarse grasses there, nitrate responsive, along with a significant number of nettles, thistles, and there was absolutely no broadleaf in it whatsoever. The most southerly one, we'll call it pasture, was arable up until 2002, been intensively farmed, and under a countryside stewardship scheme it was reverted to meadowland. The land was ploughed, sewage sludge went into it, and a meadow mix was applied. And now there is a good range of grasses, legumes and wildflowers in it, and it's quite productive. Adjacent to the east is an arable field which has largely been into continuous cropping, although 20 years ago about a third of it was down to permanent pasture. Well, there's the shed that you'll see in some of the film. There's the A15 where all the noise comes from. That's where the worm samples were taken, 10 paces either side of the hedge here. That's where the soil samples were taken in the arable field, again 10 paces in from the hedge. We're 10 paces in from the boundary of this grass field. On the other side is an arable field. 8 years ago this was also arable, although it's set aside, and since then it has been grazed by cattle. The grazing has taken place on a mob grazing basis. I put them in, get them to chomp it down and then move them on to another patch to allow fresh regrowth. What we're going to do is sample the soil here, dig down and see what we find. We'll do 4 digs over a square yard area and count the worms. And then we'll go the other side of the hedge and do the same thing. We're now on the other side of the hedge, 10 paces in. As you can see, this is an arable field. Last season had oilseed rape on it, and it's recently been re-drilled with wheat. To the best of my knowledge, this field has been in arable production for over 40 years. It's been well managed in accordance with RB 209, and it's had very good yields, 3 to 3.5 tonnes of wheat per acre. So let's dig here and see what we find. There's one. So what did we find from the sampling? Well, on the pasture, the grass side of the hedge, it works out that there were some 750 worms per square metre, and on the arable side there were 300 worms per square metre. So the difference is that there were 60% fewer worms on the arable side. And that, I would suggest, would be also an indication of the differences in the levels of biodiversity. However, what we'll do is dig even deeper, and we're going to sample the soil on both sides and see what else we can find. The soils in each of these 3 fields has been sampled over the last 9 years for the soil organic matter or carbon, and also for trace elements. And in 2002-2003 the figures were as follows. For the meadow field, the soil organic carbon, I'll explain that in a minute, is 6.6%. 2002 the grass was 4.2%, and the pasture that was in arable conversion was 1.5%. 2005 it went up to 1.9%. In 2010 all 3 plots were resampled again, and the meadow had increased to 7.5% soil organic carbon. The grass had gone up to 5.6%, and the pasture, the one that's in conversion, had increased to 2.3%. At the same time I sampled the arable field, and that was 1.6%, 1.4% down there, and broadly equates with the same figure that you see down there in 2002 for the field that went into conversion. Now, in terms of calculating the amount of carbon in the soil, a big issue is the bulk density of the soil, and the range is quite significant, so you can be readily out by a factor of 2 in terms of calculating the amount of carbon there. So in the end I was obliged to turn around again, take further samples 10 paces either side of the hedge. These soil samples were weighed and then dried and the bulk density calculated. A word on sock and song. Soil organic carbon is fairly straightforward. Take a sample of soil and then, using a process of oxidization, either a wet one with an oxidant or by ignition, measuring the carbon dioxide, you can calculate the carbon. And it was the latter process that was used in respect to the sampling that we've been looking at so far. Soil organic matter is a far more complex issue. Soil organic matter comprises of all the living organisms in the soil. It's all the animals, it's all the worms, it's all the microorganisms, the bacteria, the fungi. In addition to that, it's all the decaying organic material. It also includes the humus. Now, soil organic matter is being described as a sort of black goo, and that partly explains why soils that are high in soil organic matter are darker than ones that are at a lower level. But the role of soil organic matter is quite magical. It's responsible for breaking down all that material to release the nutrients in a form that can be readily taken up by the plants to then go around the cycle again for further growth. Soil organic matter is measured by calculating the soil organic carbon and then multiplying by an amazingly precise 1.72. Now the next 2 slides show how I calculated the soil organic carbon in the soil. If you wish to study them, I suggest you pause on the 2 slides. The soil organic carbon figures per hectare work out as follows. For the meadow, 225, for the grass, 168. You notice that that is quite a significant difference given that they're on identical soil types. That difference actually has decreased from 2003-2002, when the difference between the soil organic carbon levels was actually 50%. Doing some research, the only explanation that I can give for that, or suggest for that, is that associated with the application of nitrate fertilisers. Nitrate fertilisers increase the microbial activity in the soil, which in turn consumes more soil organic carbon. And it would appear to be the case that the application of nitrate fertilisers, the increased microbial activity, actually results in a loss of SOM despite the above ground increase in biomass that's been achieved by the nitrate fertilisers themselves. Another factor in there, of course, is ivermectins associated with impacting negatively on microbial activity. On the pasture field at the bottom, it's 69 tonnes, and in the arable field, 53 tonnes per hectare. With those figures, we can then work out what the actual change is between the 2003-2010 figure, 7 or 8 year period. And the figures work out as follows. For the meadow field, it's 3.8 tonnes of carbon per hectare per annum increase. For the grass, it's 5.2 tonnes. And for the pasture, the one in conversion at the bottom, it's 3 tonnes of carbon per hectare per year. Now, I have to point out that these figures are somewhat at a variance to those that are generally accepted. And indeed, they're between 5 and 10 times higher than the typical figures that are used, usually in the range of about 0.2 to maybe 1 tonne of carbon per hectare per annum increase on pasture land. So what are the possible factors then for this higher sequestration rate that we're seeing? Well, an obvious one is dodgy sampling there, analytical error, and also that of stone. But on the analytical side, the figures actually over the period have been quite consistent, and the carbon figures for the arable land are broadly in line with the accepted data. Stone, I didn't include in the samples anything over half an inch. Small samples of big stone would make a big difference, but the soil types were the same, so the impact of stone may change the total carbon figures. It would not change the ratio. Obviously a big issue is that no chemicals, nitrogen in particular, were applied and no pesticides, so there was no interference with the soil ecosystem. In 2002, all 3 fields were sampled for trace elements and then optimised for up to 15 trace elements. These trace elements not only included P and K, but also some ones that are not typically considered: calcium, copper, boron, zinc, sodium, iodine and selenium. And these trace elements could be quite a significant factor in that they not only improve plant health, think the impact for instance of copper, but they also increase the yield. With improved plant health, that knocks on to livestock health and also their fertility. And indeed on this holding we've got 100% fertility each year, and all the cows calve in a 3-week period. The improved health of the cattle means their immune systems are up to speed, and there's evidence that with this approach there's a significant reduction in the susceptibility to TB. But also because the plants are healthy, high in trace elements, it also produces healthy food which has a knock-on to human health. The meadow and the grass fields, the top 2, are actually quite high in calcium, and research indicates that high calcium levels increase the rate of carbon sequestration within grassland. Also, manure has been regularly applied to each of the 3 fields. However, there has been a net import of organic matter to those fields there, because the straw has been taken largely from the field next door actually, and so arguably there's maybe a 50% increase in manure application over and above that which you would have by a closed loop system. All 3 fields have been mob grazed, and by that I mean they've been put into a confined area, they graze it down, they moved on to the next one, which has the effect of invigorating the growth on that pasture, and arguably it will have an effect on the root system as well. Now the Australians have been quite keen on looking at this area as a means of counteracting climate change and also increasing their soil fertility. In this instance, off one of their websites, it's Zimbabwe, and there's a comparison here between 2 locations in the same area. One has been randomly grazed and this one has been mob grazed. In other words, the only difference between these 2 in terms of inputs is the way that the cattle have been managed. No nitrogen has been applied. Now, there appears to be quite a big issue in terms of the carbon and nitrogen balances in soils, and what the impact is on that I don't know, but certainly there has been an increase in legumes, both on that grass field, the middle one, and also on the one that went into conversion. Then we have synergy. The whole is greater than the sum of the parts. In other words, all these various management practices here have combined potentially to give us that significant increase in carbon sequestration over and above that which would normally be accepted. With that 3 tonnes per hectare per annum figure in mind, let's backtrack a fraction and take a look at the per head cattle methane emissions. It works out that a beast, a cow, will emit 50 kilograms of methane per annum. Using a 100-year figure for the CO2 equivalent, that works out at 1 tonne of carbon dioxide equivalent per annum. And as you probably gathered, I think the 20-year figure should be used, and that works out at 3.6 tonnes of carbon dioxide equivalent emitted per beast per annum. Now what that means is that soil needs to sequestrate 1 tonne of carbon per hectare per year to absorb 3.7 tonnes of carbon dioxide equivalent. Now if we turn around and take a stocking density of one animal per hectare, which is about what we have here, it works out then we've got 3 tonnes of carbon being sequestrated per year, the lower figure, deduct the 1 tonne of carbon associated with the emissions of methane from the animal, and that leaves us with 2 tonnes of carbon being sequestrated per year as a benefit. Bring that back up to CO2 equivalent, and it's 7 tonnes of CO2 equivalent benefit per year from managing the pasture land in the way that we are here. As we move in under the trees, you'll notice that the grass in this meadowland is becoming thicker under the trees. Now this is counterintuitive, given that the grass here is in the shade of the trees, less light, and also one would imagine that the trees are also drawing more moisture from the soil. There is one fundamental difference between the soils in the field and under the trees, and indeed in the shade of hedges, and that is that the soil organic matter is higher. It would appear therefore that the grass here is benefiting from the higher soil organic matter levels. We've just done the baling in the field, and what we've done is measure out 15 metres 50 feet from the hedge line where there are the trees, and then gone another 50 feet 15 metres on from there, and we've counted the bales each side, and there are 34 bales in the strip from the hedge to the 15 metre mark, and then there are 28 bales from the 15 metre mark out to the 30 metre mark. i.e. there's about a 20% difference or so greater under the trees than the next strip out into the field. If one was to check fields of wheat, barley and so on, you're going to see a similar effect. In this shot you can see that the wheat under the trees is greener and higher by about 4 inches 10 centimetres than in the main crop out in the field. This effect is nothing new. Every garden knows that by increasing the soil organic matter by applying compost or manures, you increase the yields. This small veg plot is part of a paddock of some 2/3 of an acre, a quarter of a hectare. It produces vegetables for us for most of the year. The paddock contains a small orchard of some 40 fruit trees, which produce tons of pears, apples and plums that keep us in fruit from mid-July to early May the following year, along with plenty of cider and perry. Furthermore, the fruit trees, being of traditional rootstock, also permit undergrazing, and we keep some 4 Lincoln Longwool sheep, and they've had 6 lambs this year. They're on the paddock for probably 50% of the time, so the yield in terms of lambs, let's call it 2 per year. A dozen or so chickens are fed largely on scraps and obviously the grass as well, and these produce 10 a dozen or so eggs per day. This paddock then, in addition to producing all that food, is also part of an ecosystem. There's some 25 species of bird that you see throughout the year. There's a couple of pairs of bats, the toads, the frogs, all the insects associated with the grass and the trees. However, the input of this stuff to the system is pretty close to zero. And you'll recall from the elevator brief that if the input of fossil fuels is low, then it means that it's going to be high on manpower, and in this instance, quality jobs. But not only that, the trees, the grass and the soil is also stashing away the carbon. The cattle, pigs, sheep and fowl are not only eating the byproducts or the waste and grazing the grass, at the same time they're also increasing the soil fertility, and as such are an integral part of a low carbon mixed farming ecosystem. With that in mind, now let's go and take another look at that arable field. On the other hand, if that same quarter of a hectare was farmed intensively as monoculture arable to produce wheat, there would be high levels of fossil fuels for the machinery to cultivate it, for the combine harvester, for the drying, and also of course fossil fuels are required for the production of the nitrate fertiliser and the pesticides. And then at the end of that, this quarter of a hectare would produce 2, maybe 2.5 tonnes at best of wheat. Of course, there is all the other biodiversity that goes along with this that you can see. DEFRA does, however, require as best practice 2-metre grass strips around the edge of this field to improve the environment. Well, with that in mind, now let's go and take a closer look at those soil carbon figures. The wheat field has 53 tonnes of carbon per hectare. That might be contrasted with the meadow field, which had 225 tonnes of carbon per hectare. You notice there's a 4-to-1 ratio difference between those two. Now, given that intensively reared cattle are going to be fed on combinable crops as part of their feed, barley, wheat, maize, soy and so on, an interesting question is, what is the rate of decline associated with the arable practices here, and what might be attributed to the intensive rearing system by way of further greenhouse gas emissions? Quality data on carbon and soils is, to say the least, sparse. However, the UK does have some figures for the changes between 1980 and 1995, and this survey identified that there was an 18% reduction in soil organic carbon over that period. Also, it identified that in permanent grassland there was also a 16% reduction in organic carbon, which quite frankly I found a little surprising, and my research would suggest that possibly a significant factor in that is actually the application of nitrogen, as I've already described. If we extrapolate these figures over a 40-year period, then it amounts to a 40% loss of soil organic carbon over that period. Now that assumes it to be a linear process, which is what IPCC do. But is that valid? With that 40% figure in mind, let's just have a quick look at biodiversity. DEFRA used birds as an indicator of species as to the health of ecosystems, biodiversity. And on farms in the UK over the last 40 years, there has been a decline of 40% plus in those farmland birds. Now, there's also been a decline of 40% plus in soil organic matter. That fuels the whole food chain at the bottom. And it's a question that must be asked that despite the fact there are obviously issues associated with increased predator birds, loss of habitat, nesting opportunities and so on and so forth, if we're looking to improve the situation by way of biodiversity above ground, then maybe we should be looking at issues associated with replenishing the soil organic matter below ground. The effect of land use change on soil organic carbon is pretty well documented, and as I explained in the Energy and Climate Change brief, the changes from grassland to arable results in a significant early reduction in soil organic carbon and then a plateauing out. And the biggest reduction is actually during the first 20-year period. This slide shows UK wheat production over the last 40 years or so, and you can see that it was broadly plateauing up until the mid-1970s, green revolution in inverted commas, increased genetics, improved combine harvesters and other management practices, use of fertilisers of course, over the following 20 years or so resulted in a doubling of wheat yields from 4 to 8 tonnes per hectare. However, for the last 15 years or so, wheat, or indeed all crop yields, have largely plateaued, as you can see here. Now, what's intriguing is if you now superimpose that hockey stick for the loss of soil organic matter on the same graph, and you can see that there is obviously an initial decline over the first 20 years or so. Now, during that loss of soil organic matter, there is also a release of nitrogen, and for each 1% loss of soil organic matter, there's a release of about 33 kilograms of nitrogen per hectare. In addition to that, it was being applied by way of chemical fertilisers. Also, there's a release of other essential nutrients that go along with each of the 1% losses in soil organic matter. Now, if we turn around then and use the figures in terms of the differences between the meadow field and the arable field over the 40-year period and calculate out what has been the loss per tonne of wheat produced over that period, the figures are here. But what it actually boils down to is that for every 1 tonne increase in wheat yield over that 30-40 year period, there has been 2 tonnes of CO2 released by way of carbon from our soils. Now, in order not to over-egg it, because we don't know exactly where that initial loss in terms of soil organic matter took place, we'll halve that figure and say there's been suggest that there's been a 1 tonne release of carbon dioxide for every extra tonne of wheat produced over that 40-year period. Interestingly, DEFRA have recently put out a project to identify why we've got the yield plateau, and they're looking for genetic improvement. I said for each economic activity we would take a look and consider how 50% energy savings might be achieved tomorrow. Let's just have a look at what's involved in overseas sourcing of beef. Here's a report from the Brazilian government indicating that cattle farming is responsible for 80% of the deforestation that's taking place in the Amazon. It amounts to 1 hectare every 18 seconds. 40% of all UK processed meat comes from Brazil, and 90% of that comes from 3 companies, Burton, JBS and Marfrig. Greenpeace have linked Tesco to beef and Amazon deforestation, although Tesco's deny it. The NBA News report that JBS, one of those 3 big exporting companies, has just avoided a £2 billion Brazilian real fine for processing beef from prohibited areas, i.e. the Amazon jungle, and from holdings using slave labour, by volunteering to sign up to an agreement basically not to do it. Here's another one from also the NBA, National Beef Association News. Tesco started importing its beef from 4,000 miles away in the States, calling it Black Angus beef. There's issues there over the identification of those, by the way, we won't go into that. And basically it's seeking to undercut Waitrose, which is procuring its beef, or its Angus beef, from British sources. Now, an interesting issue there, of course, is the whole issue of hormones. 80% of all livestock in the United States receive hormone injections to increase the rate of growth, and the EU has banned the use of these hormones. Tesco insists that it ensures that its US beef is hormone free. Whilst we're on Tesco, they've started introducing what they call zero carbon stores. Well, possibly they're zero carbon, but that's ignoring, of course, all the carbon associated with farming, the processing, packaging and transport. Also a report from the Daily Mail in March, claims by the big supermarkets, Tesco's and Sainsbury's, to be fueling the economic recovery by increasing the rate of employment, proved not to be the case. Over the last 2 years, the number of full-time jobs offered by Tesco and Sainsbury's has actually fallen. Let's take a look at energy use in beef production. Here's a figure from the National Geographic magazine for the United States, showing that basically each steer requires 230 gallons of diesel to be produced. In my own herd here, which is only pasture grass fed, it works out at 25 UK gallons per steer. Almost a tenfold difference between the two. From this, you'll have guessed how you can achieve your 50% reduction. Basically, it's shot locally. The benefits are, you've got a good chance of knowing where it's come from and what's in the beef, or more likely what's not in it. You've got very low transport costs. If it's largely grass or pasture fed, it's going to be high in omega-3. It also ensures you're going to enhance the rural landscape and biodiversity. You're going to get increased soil organic carbon levels, which then has an impact on climate change, and with that goes flood and drought mitigation. You're going to get genuine job creation, you're going to boost the local economy, and you're going to get increased food security. And the only point I'd add to that is make sure your butcher's hanging for at least 2 weeks if you really want some quality beef. Summary. Grassland soils have a huge pool of biodiversity and a greater soil carbon pool than tropical rainforests. And soils are the largest pool and sink of carbon and are critical to atmospheric regulation. So what are the challenges to the thinking? I have to say there are a few more than I expected when I started on this project. Well, first of all, the point that a 1% increase in grassland soil organic carbon mitigates the global fossil fuel greenhouse gas emissions. Grassland absorbs more CO2 equivalent than pasture-fed cattle emit by way of methane from enteric fermentation. Livestock are actually necessary for maintaining grassland, biodiversity and soil fertility, and they're also an essential part of sustainable mixed farming ecosystems. By including natural cycles in their emission calculations, Kyoto actually discriminate against sustainable farm practices and are furthering ecosystem degradation. And it follows from that then that the methane and nitrous oxide emissions associated with those natural cycles should be excluded from the calculations. Climate change and land management policy priorities should revolve around soil ecosystems. First of all, to reverse the ongoing degradation and to reduce further emissions of greenhouse gases. To also maximise the soil organic carbon sequestration, and also to reinstate soil ecosystems, hence fertility and productivity. And last but not least, to reverse biodiversity or ecosystem decline. In short, we should be looking for an integrated approach to the whole carbon cycle, recognising the key role of soil. This brief has highlighted the importance of grassland, both as a store of carbon, but also as a mechanism for recovering carbon dioxide from the atmosphere. The switch to monoculture, or arable farming, over the last 40 years has resulted in a doubling of our cereal yields. But a comparison with the adjacent arable field to the pasture land that we're on has suggested that that increase in cereal yields has been at the price of burning carbon in our soils. And it suggests that for each tonne of cereal, there's been a burning of about 1/3 of a tonne of carbon, which amounts to a tonne of carbon dioxide being released into the atmosphere. On the other hand, the cattle, both by grazing and pumping out this stuff, and then it being incorporated into the soil by the worms, enhances the soil ecosystem and also increases the above ground biodiversity. For a solution then, it suggests that the focus of our action should actually be on soil management. Soil is where we have the largest stores of carbon and part of the carbon cycle, and also as a means of stemming the further releases of carbon from our soils, and also for recovering carbon dioxide from the atmosphere. Rather than cattle being part of the climate change problem, they're actually part of the solution. Beware single issue environmentalism.